You are able to see it. This is a lecture on vibration transducers. As you know, in condition based maintenance, about 70% of the cases of machinery health monitoring is done usually through vibration. So, in this class we thought that we should look into the merits and demerits of the available vibration transducers, and what are the different types of vibration transducers used in industrial health monitoring, and in the subsequent classes we will be talking in details regarding how actually vibration monitoring is done. So, as you know what is vibration, you all know vibration can be represented either as displacement, velocity or acceleration. Well, if displacement is denoted, the amplitude is denoted as A, velocity is omega A and acceleration is omega square A. So, you see there is always a strong relationship between the amplitude of the quantities measured and the frequencies. So, in one way, at high frequencies you will see, because of this omega square A term, the acceleration is going to have a high magnitude compared to displacement. Displacement is actually a frequency independent phenomenon, okay, and it is actually a low frequency phenomenon. Okay. I always am asked this question, what is the best parameter to measure? Okay, you will see as we go through this class, sometimes at low frequencies it is actually the displacement. For example, if you think of a shaft, okay, which is there in a casing, this is the casing of the shaft or a housing. What could happen is, this shaft while rotating, if it is not on the rotating at its center, there may be a subtle slight eccentricity, okay. And because of this, at any of the points you will see that displacement at one location is A 1 and another location is A 2. For the shaft to be uniformly or concentric to the center, all these A's should be equal if you measure in the four quadrants or four directions, okay, at 90 degrees to each other. But if you will see A 1 is not equal to A 2, is not equal to A 3, etc., okay, then then what happens is we know there is some problem, okay, because of eccentricity. And how can this be detected? If I have some sort of a sensor here, displacement sensor or some sensor which senses this gap between the rotating shaft and the casing, it will tell there is something wrong with the machine. So, this is where actually displacement sensors are used. Okay. We could be slowly turning the shaft, it may not be powered by a motor, we could be slowly rotating by some mechanical device. Think of a large cement plant where we have a large very long rotary kiln. Kiln could be of the diameter of 2 to 3 meters, the diameter of the kiln. Okay. And this could be about about 2 to 3 meters in diameter. So, what happens in such a case, if there is a slight eccentricity, we are going to have problems in the forces, unequal forces, etc. So, this actually you would have seen when they go to install and commission such equipment, they actually put a lot of dial indicators. Okay. These are nothing but mechanical spring loaded, they have a plunger and stylus. So, the plunger is going to move depending on this A 1, A 2, etc., and then we will have a corresponding reading. And these dial indicators are very good in the sense, if you want to measure the surface roughness in a bearing to out of roundness in a bearing. The small variations here could be measured by a dial indicator. Okay. And this could be in the order of microns. Okay. So, to measure displacements, we have a mechanical device. A dial indicator looks something like this. This is spring loaded. This is the plunger. So, as you will intuitively see that if the motion is very slow, almost close to static, I can use a dial indicator to move the see the displacements. But imagine if the bearing or the rotating shaft was moving at a very high speed. Because of the inertia in the plunger, this plunger is not able to respond to quickly changing stimulus. So, the need for high frequency measurements arises, and that is where our dial indicators or LVDTs, another linearly variable displacement transducers, have a limit in the frequency range as to how much they can measure. Okay. I mean, for low speeds they are good. In fact, LVDTs are good for less than 50 hertz. Okay. But imagine I want to monitor the vibrations of a gas turbine. Gas turbine could be having the about close to 30,000 RPM. So, 30,000 RPM will become 30,000 by 60 is about 500 hertz. Okay. And that will be the fundamental frequency. So, such a high speed measurements are not possible through mechanical devices like an LVDT or a dial indicator and so on. So, we have to see what are the instruments or transducers available to measure high frequency vibrations. Okay. Before I go into that, let me just give you a general overview of what are the different types of vibration transducers available for us. One is the piezoelectric accelerometers, and we will be discussing in details regarding the piezoelectric accelerometers, because 99% or 98% or 95% of the vibration transducers are actually piezoelectric accelerometers nowadays, because the convenience of measuring omega square A, which is acceleration, is very easy. And then once I have this accelerations, I can divide it by omega to get velocity and divide it by omega square to get displacement. So, this covers the entire frequency range from 0 or as close to 0 to about 5,000 10,000 hertz, which is not possible with the LVDT or the dial indicator we just discussed. Okay. Of course, another one is the LVDT. And then one thing you would notice that be it an LVDT or a dial gauge or for that matter an accelerometer, they have to be always in contact with the surface at which we are measuring the vibration. Okay. But there are instances where we cannot touch this surface. For example, the surface is so soft, surface is so hot, temperature is very high, surface is not accessible, okay, a very minute location in a very intricate position. We cannot use an accelerometer or an LVDT. So, that is where we have to use certain laser based techniques, be it to measure the normal vibration or the rotational vibration. Of course, there are some probes like the eddy current proximity probe, which can be used to measure the gaps or the it is like a non-contacting type of transducer. We can measure the displacement or acceleration in such or velocity in such cases. The eddy current proximity probe and moving coil velocity pickup, they essentially measure the velocities and then they are non-contacting in nature. But one again disadvantages of the eddy current proximity probe or the moving coil velocity pickup is that they cannot be measured on surfaces which are non-ferritic. Surfaces has to be ferritic to measure the eddy current or the, to use the eddy current or the moving coil velocity pickup. So, let us come to the brief principles of operation of a piezoelectric accelerometer. Essentially, what the piezoelectric accelerometer has is, basically if I put these crystals, piezoelectric crystals, either in this form, either I compress them or I shear them, they are going to develop a generate a force, and this force is responsible for generating the charge Q, and this charge could be converted to a voltage with a suitable charge to voltage converter amplifier, and basically I will get the voltage signal. These are known as the charge type of piezoelectric accelerometer. What happens here? Suppose I make this accelerometer here. This is mounted on a surface. Okay, wherein it is having a certain motion x. So, essentially in this piezoelectric type accelerometer, all I have is set of piezoelectric crystals mount within certain disk, and they are bolted. Okay. And then I will get a charge Q, which is proportional to the displacement of this seismic mass. This Q is proportional to y minus x. Okay. And with mathematical equations, you will see eventually this Q is proportional to the base motion. Okay. Motion could be in the form of acceleration. So, once I get this charge, as you know, charge cannot be stored, charge will decay with time. So, immediately we have to have a circuit wherein this charge has to be converted to voltage. Okay. So, this is where a piezoelectric charge type accelerometer would require a charge to voltage amplifier. Okay. This amplifier is outside the accelerometer. Okay. The advantage of thus the charge type accelerometer is, and this is a sealed unit, this is a sealed unit. Advantage of such accelerometer is this can be subjected to very high temperatures, the charge type of accelerometers. Okay. But the disadvantage is that you have to carry a charge to voltage preamplifier with this accelerometer. So, with the miniaturization of electronics, what has happened is people have put the amplifier inside the accelerometer. Okay. In a small IC chip. Okay. But then to power the accelerometer, I have to give it a power source. It requires a power source. Okay. So, once such accelerometers are there, then what we can do is, so this is the same accelerometer, but the IC chip is installed inside the accelerometer, and all you have to do is just take a cable, and this is a voltage output, because you have to, the same cable could be used, another conductor could be used to give the power supply to the IC, which is used to convert the charge to the voltage. But the disadvantage of this is, because the IC chips are integral and kept inside the accelerometer housing, and usually this housing is stainless steel, very hard, and you can never break it open. Okay, they are hermetically sealed. So, this accelerometer cannot be subjected to high temperatures. High temperatures, we cannot subject them to high temperatures, because this IC chips will be get damaged. But for simple vibration measurements in the room where the ambient temperature is 30 to 40 degrees or around 30, 35, 40 degrees Celsius is good. They are not good beyond 100 degrees Celsius. The ICP type, there are many trade names for this, like you will have the ICP types, the deltatron, piezotron, isotron. This tron comes from the electronics, okay, and delta, piezo, iso, ICP. These are different trade names the companies use to sell their charge amplifiers, which have the IC inside it. So, all you will require is just put that accelerometer, give it a power supply, and you will straight away get the voltage. So, this is very convenient from a vibration monitoring point of view, because nowadays many of the signal analyzers have the built-in power source, which could be used to power such ICP type accelerometers, and they are very convenient. But the strongest disadvantage is that they cannot be subjected to high temperatures. In fact, while doing experiments on measurements on very high speed gearboxes, I have lost couple of accelerometers because the technician mistakenly put the ICP type accelerometers on a bearing which was very hot, and we are monitoring for about 30-40 minutes. End of the day, I get no signal, and see that the IC chip has got fried, okay, because of the high temperatures. So, we have to be careful when using such ICP type accelerometers. Okay. We will go to the details of the accelerometers later, but let me just tell you about the other important accelerometers or vibration transducers. And this is how actually in the inside of the accelerometer, this is how it looks like, and this is the mass which is loading it, and this is the piezoelectric crystal, okay, and this is a tightening bolt which goes, and this whole unit is sealed. This is a ceramic unit, there is a steel unit, and this is sealed, and because of the relative displacement here and the piezoelectric mass, we will get a charge which is proportional to this displacement or acceleration, and then we will see a voltage, and this voltage could be measured as the other. So, the charge sensitivity could be usually picocoulombs per meter per second square, okay, or in the ICP type it will be the voltage sensitivity millivolts, usually meter per second square. Okay. I will move on to the, and this is how the typical piezoelectric accelerometers look like. If you will see, this is the size of a 50 paisa coin, and this is where you connect the cable to connect the charge to measure the charge which has been generated, and similarly this is the top connector, this is a side connector, okay, and this is what is known as a triaxial accelerometer. Triaxial accelerometer. Because of the fact that acceleration is highly directional. So, at any one point you would see in a machine that we have to measure in the x direction, in the y direction, in the z directions. So, rather than putting 3 uniaxial transducers in one location, the 3 piezoelectric crystals are put at one location, and then we can see this means I am measuring in the x direction, this is perpendicular to x in the y direction, and this z is out of the plane of the projection, and so then I get the 90 degree 3 directions which are 90 degree perpendicular to each other or mutually perpendicular. And if you see this hole, this is just a hole to mount the accelerometer at the location just by tightening a screw, or you could have you could put studs like this on the accelerometer and then tap a hole on the surface where you are measuring the acceleration, and then we can measure the acceleration. Another very important note you have to make while using these charge accelerometers is the cable. Cable plays a very important role, because this conductor which is there, and there is a signal wire and the ground wire, and if there is a relative motion between them, they are going to generate a charge. Okay, suppose the cable is violently moving, having motion, and this cable is laying on a surface which is having excessive vibration. Then you have your accelerometer here. Is having this accelerometer here, and then there is excessive vibrations. Okay. Now, because of this cable is going to have a lot of motion, and because of this motion there will be charge generated, which is not actually a charge due to the acceleration, but charge due to stray noise. So, a lot of stray noise will occur if I do not take good care of the cables. So, these cables are very special cables, okay, and they reduce what is known as the triboelectric noise, and a good way to do that, to reduce triboelectric noise, is to ensure that the cables do not whip around or slash around or. Okay. So, what you have to do is, if you put this accelerometer here, usually you tie the cable, some sort of a tape, so that the cable does not move. Okay. Because if this is a charge type of accelerometer, okay, a lot of charges are going to get generated if the cables are going to move, and they are going to interfere with the measurement charges. And the best way is to have this amplifier, the charge to voltage converter or amplifier very close to the accelerometer. Okay. And usually these cables are not very long, about 1 meter to 3 meter maximum, because beyond that the cable noise will be so much that you will contaminate your vibration signal. So, this is another precaution you have to take while using the charge type accelerometers for measurements, vibration measurements. But these kind of issues are not there when you take when you have the ICP type of accelerometers, wherein we straight away get a voltage signal in the cable rather than charge. Here we have the charge, okay, and charge will decay and charge you are generating. So, you have to have the charge to voltage amplifier. In fact, as soon as the charge is generated, you have to convert it and then transmit over long distances, because sometimes if you have to measure at one particular location and record at maybe 100 meters away, okay, you cannot have a 100 meter triboelectric cable which is slashing or moving around and then generating a lot of noise. So, your vibration measurement will be no good, and that is where you have to be careful of it. And you can get a feel of how large or how small these accelerometers are. Obviously, to increase the sensitivity of the accelerometers, we have to have more piezoelectric crystals. So, more piezoelectric crystal means heavier it will be. So, heavier accelerometers will have high sensitivity. Usually, typically this kind of accelerometers which you see in the palm of somebody's hand, it is about 10 picocoulomb meter per second square. and if you have the right type of voltage converter, this could be about 10 millivolts per meter per second square. Okay. There are accelerometers wherein we have to measure very low levels of acceleration. For example, a floor vibration wherein you have put an tunneling electron microscope or a scanning electron microscope. The vibrations level could be about 10 to the power minus 6 G, micro G's, microgravity levels. For such measurements, we have to have maybe transducers having 1000 millivolts or 1 volts per meter per second square. So, this calls for very massive amounts of piezoelectric crystals. So, whenever you have high sensitivity requirements, the transducer will be big and heavy, but you have to pay a price for the transducer being big and heavy. The frequency response will be low. So, we obviously cannot measure very high frequencies with high sensitivity accelerometers. This could be the frequency of such heavy accelerometers could be up till maybe 10,000 hertz. Suppose I want to measure very high frequency vibrations. High frequency vibrations. To measure high frequency vibrations, my frequency response of the accelerometer has to be very high, maybe about 7200 kilohertz. So, they have to be very lightweight. So, the sensitivities are very low, maybe 1 millivolts per meter per second square. Okay. We want to measure accelerations, very high accelerations, for example, during a shock generation, something fell on the ground. So, in such a case, and shocks are usually very high frequencies. So, we have to use light accelerometers. So, if you go to the catalog of any manufacturer, you will see different types of accelerometers made available to you, whether so if I was to just specify the generic specifications of an accelerometer. By accelerometer, I mean piezoelectric accelerometers, and that is what we are going to discuss. One, of course, it is sensitivity, whether it, and of course, before that could be the type of accelerometer. By type, I mean whether it is charge or ICP type, where the electronics is inside. By sensitivity, it could be whether it is in picocoulomb per meter per second square, if it is the charge type, or millivolts per meter per second square. Next important is the frequency response. By frequency response, I mean that every transducer is also a mechanical system. So, this is also going to have its natural frequency. Okay. Maybe, so measurements up till this range about 0.7 times, if this is its natural frequency, 0.7 times Fn. So, this is the useful range wherein, or this is the useful range. Wherein you will measure the. So, this accelerometer is good only up to 0.7 of Fn. Okay. Then, of course, the other maximum temperature it can be subjected to. It can withstand. This is very important, because when you talk about industrial health monitoring, there will be gearboxes and bearings which are subjected to very high temperature, maybe 300-400 degrees Celsius. Okay. Maybe you should know from the manufacturer whether the accelerometer can be sent or subjected to such a high level of temperature. The directional sensitivity. whether the accelerometer is sensitive to which direction. So, we have to mount the transducer in that direction to which it is highly sensitive. It could be uniaxial or triaxial. And then of course, subjected to it should not get affected by nuclear radiation, by EMI, by moisture. Okay. Does it require external power supply or not? Its mounting methods, okay. And so, if you, and of course, the very important is the mass of the accelerometer. Because as you know, vibration is a very important dynamic property of a system, and the dynamics of the system is going to change if the mass of the accelerometer is larger than the mass of the system which whose vibration you are measuring. It is going to influence it. Imagine we have a very thin disk, okay, which is rotating or which is having a motion, some sort of transverse motion, okay, and this disk maybe weighs 100 gram. Okay. I obviously cannot put an accelerometer on this which is weighing 500 grams, okay, because the entire dynamics of the system is going to change. So, one rule of thumb which you have to always keep in mind, that mass of the accelerometer has to be less than 1/10 of the mass of the system on which you are placing the accelerometer. Okay. Otherwise, this is what is known as the mass loading effect will occur, and then you are not going to get the true reading of the acceleration. Okay. Now, before I continue more on the accelerometers, I just want to mention you about a couple of two important probes which you also use, and this is essentially an eddy current proximity probe, which is a non-contacting probe. Basically, what happens, we have a probe here onto which we generate we apply a high frequency signal, very high frequency signal, about few megahertz, okay, and that is there in the primary of this. There is a coil here and primary, and because of this high frequency waves which are close to the shaft, which is iron shaft, eddy currents are going to get generated, and this eddy current will be generated in this gap. And so, the secondary voltage which is sensed by this proximity probe will be proportional or will be a function of this eddy current, and this eddy current is a function of the gap. So, we can measure such eccentricities or gaps which are created between the shaft and its journal or the casing because of an radial runout eccentricity by putting such eddy current probe. Okay. They are non-contacting type. Of course, they have a very low frequency response compared to the accelerometers, but the advantage is I obviously cannot put an accelerometer here, because accelerometer is only going to measure the vibration of the casing here. I can no way measure the vibration of this shaft, because I cannot put the accelerometer in contact with the shaft surface. So, the relative displacement can be easily measured by such eddy current proximity probe. In fact, many of the steam turbines, etc., they come up with this pre-installed with 2 or 3 eddy current probes, and if this is your x and this is your y, if you plot them x and y, and if they are identical and of the same frequencies, you will get a perfect square. Okay. So, sorry, perfect circle, and these are good for what is known as orbit analysis. Okay. And if there is just looking at a phasor diagram of the x and y on a two plane system, you will see if it is a perfect circle, you know this system is concentric to the casing and it is rotating perfectly. And with time this may change like this, okay, this may change like this, and then you know that something is wrong with the eccentricity of the shaft, and this is a very good way to report it or record it or observe such eccentricity by having an eddy current proximity probe. So, usually in steam turbines, large compressors, axial, we can put such eddy current proximity probe to measure the relative motion between the shaft and the casing. Another non-contacting type transducer is the velocity pickup. Essentially, there is a permanent magnet and a moving coil, and because of the motion of this system here, I am going to get an EMF. Okay, and this motion is because of this is contact, this is in touch with the surface, okay, the velocity type pickup, and this will get a velocity proportional to this EMF which has been generated. But modification to this is, if I have something moving here and this coil is not there and this is ferritic, we can have a key phasor kind of signal. It will give a signal like this. So, these are also used to measure rotational speed. Because with vibration health monitoring, you know, measuring the rotational speed is also very important. Okay, I cannot obviously put a tachometer always to a rotating shaft, to an end of a rotating shaft, but if I have an arrangement like this, wherein I have a shaft on which there is a keyway or a key, and then if I put such a pickup, so at every time the keyway comes below the pickup, this voltage, this gap is going to change. So, there will be a voltage generated with time. So, just measuring the time period, I will know the frequency of rotation as the inverse of the time period. Just by having a frequency counter, I can measure the rotational speed. And in the industry, all such rotational speed measurements is done through an inductive pickup. Okay. And then you can transmit this signal over many meters or kilometers for that matter. Okay. And on real time, always you will have this RPM trace. Okay. Now, earlier days, you know, when the piezoelectric accelerometers were not developed, people were using such moving coil kind of velocity pickups, okay, and eddy current pickups. But nowadays, with the piezoelectric accelerometers available, we have only two important parameters which you need to measure. One is acceleration, another is the rotational speed. So, these are the two most important vibration, though rotational speed is strictly not vibration, but I am vibration transducers, which we have to use for machinery health monitoring. Okay. I will now focus on some applications as to how this accelerometer is used and mounted on systems and so on. So, now that we know about the three types of transducers, you see this is the eddy current probe, velocity transducer and piezoelectric accelerometer. If you see their frequency range and the relative amplitude which they can measure, the eddy current probe can measure low frequency and the limit is about 2 kilohertz and the range is not much. Velocity transducer has a low frequency limit of about 10 hertz to about 1000 hertz, but the piezoelectric accelerometers can measure all the way from 0 to very high 70-80 kilohertz, and the range is also very high, the dynamic range is very high. So, that is what I am telling. To measure the acceleration, we now will be only talking about piezoelectric accelerometer. Before the piezoelectric sensing elements were used, people used to also use strain gauges instead of the piezoelectric crystals to measure the seismic accelerations. And this is how a typical chart of an accelerometer will look like. This is the frequency response, okay, and this is the resonant frequencies, and then what are the methods to mount the accelerometer, and what are the voltage and charge sensitivity as a function of temperature, etc. And this is typically which you will find in any of the accelerometers which we purchase. And the question is, we have to use this vibration measurements, and the question always you would be asking, well, I have got a certain value, is that good, is that bad, I do not know. So, there is a standard ISO 2372 standard, and recently it has been updated, and that is a newer standard I will tell you in the next class, that tells the machine's power as to the maximum permissible level of vibration in a frequency range of 10 to 1000 hertz, okay, and this is usually in millimeters per second. Okay. So, if you know a 100 horsepower machine, it should not be more than 3 millimeters per second and so on. So, that gives you a feel like when you are doing vibration measurements on machineries for their health monitoring, the power of the machine. So, the maximum acceleration or maximum RMS level in this 10 to 1000 hertz band should be not beyond a certain level, which is given in that standard. And this is how typically this is essentially a charge to voltage amplifier, and this is the accelerometer here, and this is the special cable I was mentioning about, which reduces the triboelectric noise, and sometimes you will see the cables are costlier than the accelerometer itself, because otherwise if these cables are beating around, if they move also, they are manufactured in such a way that there is so much of reinforcing mechanism in the cable itself, actually the copper conductor which is there inside hardly has any motion. It is actually there are multiple sheets of protection in this cable. There will be a layer of plastic insulation, steel reinforcement, and on top of the copper wire, and then there will be a plastic coating, sometimes silicon coating, so that it can be used underwater, etc. So, these cables are very expensive. When you are talking about underwater accelerometers or hydrophones, this we have accelerometers, underwater accelerometers, wherein you can measure the vibration of underwater structures, but the cables there are very costly. They will not allow water to creep into the or seep into the conductor and contaminate the readings, etc. Okay. And usually when we have this is an accelerometer, an uniaxial accelerometer of the top connector, and this is actually a gold plated connector here to make sure that there is no corrosion, etc. And this is that cable here, and which goes to a vibration meter, wherein you can select the knob to see the readings of either acceleration, velocity, or displacement. Okay. Now, the next question you would be asking yourself is how do we actually physically fix this accelerometer onto the surface on which we are measuring the vibration. Okay. Surface could be as soft as the flapping wings of a bee, okay, or as delicate as a buzzing bee wings, or as robust and heavy and hot as a gearbox casing. Okay. Everywhere there is vibration. How do you measure that? Okay. Obviously, on a gearbox, casing, I can mount my accelerometer many ways. One is I could attach, if this is usually the gearbox, etc., these are cast iron. So, I can very easily tap and put a stud and screw the accelerometer onto the stud. So, one is the stud, other is I can attach a soft magnet to it. Okay. But again out of my experience I am telling you, this magnets, the soft magnets are very soft. These magnets cannot be subjected to high temperatures, with time suddenly you will see that the magnet has cracked. Okay. So, usually these magnets cannot withstand high temperatures. So, usually permanently if you have to mount, you make a hole and put a stud, and then you sometimes tap the accelerometer onto it. Sometimes these surfaces are so hard, or some machine the OEM would not allow you to do any tapping, which would permanently damage the structure or weaken the structure. How do you do that? In such a case, what you do is onto the surface you glue a block. Which could be glued permanently by cement, like the cyanoacrylate, like we talk about those Fevikwik type of glues which are available in the market, etc. You can use them to glue the block onto the surface whose vibration you are going to measure. People will not ask you to let you do drill a hole and do a tapping, that is not allowed. So, usually you will use such an device, a block. Onto this block you can screw your accelerometer with a tap. Okay. And this actually the stud mounting is the best, and then comes the glues and magnetic base if it is soft, and they have pretty high frequency limits. But sometimes even just a layer of beeswax on a surface, the honey, beehive, bee wax, you can just put it here and then stick the accelerometer onto it. Okay. Just press it, and this is the bees wax. They are pretty strong. Okay. But the problem is you cannot use them beyond 40 degrees. In room temperature these are good, but beyond that they will melt and they cannot be. Another type is that if you are quickly surveying a surface, you can put a handheld probe, okay, and then move around accelerometer. Okay. Now, what I am going to do is I am going to show you some of the mounting methods through pictures. This is how the accelerometer, if you buy it, looks like in a kit. Okay. This is the accelerometer, and this is that special cable I was talking about. This is the magnet, this is the beeswax, and there are a lot of studs, washers, etc. And this is a tap given to make the tap. Okay. And this is a typical kit which you will see of an accelerometer. And then accelerometers always need to be calibrated. So, this is the handheld calibrator, wherein you can give a known levels of 10 meters per second square at 1000 radians per second, and then you will see the acceleration values. Whatever voltage it comes, it gives, you will know that it gives 10 meters per second square of acceleration. And this is typically we are measuring using a magnet here, the vibration in a test rig. And this is where another test rig wherein we have put an uniaxial accelerometer and that special cable. Okay. And this is an industrial type of accelerometers which can be subjected to very, very high temperature. This cable is special, and then we have an meter, vibration meter, which will actually see the, you can see the spectrum. Okay. These are all there in our lab. You can go to this website and see this system as well. And this is one of the reluctance type velocity pickup which we have used on the shaft. Okay. We can also use an optical encoder to measure the rotational speed, and we can use single point lasers also as an accelerator to measure the vibration, because this is a refrigerator compressor wherein we are measuring. You can see this spot here where we have put a laser beam, and once we put a known laser beam, because of the reflected wave, there will be a Doppler shift, and the Doppler shift will be proportional to the velocity of the surface, and we can measure the, for surfaces wherein we cannot approach. For example, here in another case we have a transformer which is there in our lab. You can see these points which are shining. Actually, these are the points we have put reflector tapes wherein we can measure the velocity which is with which these fins are vibrating, and then we can shoot the same laser vibrometer to measure the vibrations of the surface, because here we are measuring the sound intensity here. Another application of this laser based vibration measurement system is using a rotational laser vibrometer, okay, wherein we shoot two beams. If you can see, there are two dots. If you have two laser beams separated by a particular distance, if you know V1 and V2, if you know delta R, you can find out omega, and that is what we are using this laser vibrometer to measure the rotational vibrations. Another view of the rotational vibrometer, and this comes with the signal conditioning system, wherein we will straight away get an omega as a function of frequency. Okay. This is another view, okay, of the same rotational laser vibrometer. This is the laser head which shoots two beams. Okay. Thank you.